Okay, gang, up until this point we haven't really considered the motion of an object moving in a circle. We haven't really discussed circular motion, and I'd like to do that now if we can, sort of an appropriate time. So this is we're going to discuss uniform circular motion, and we'll have more to say on circular motion later in the year, but I'd like to at least introduce uniform circular motion. And so what we're going to imagine right now by uniform circular motion is we're going to imagine that we're moving at a constant linear speed as we move in a circle, right? So we're moving around the circle, and the speed with which we're moving, the linear speed, is not changing. So constant linear speed. So I've got this circle here, and I want to imagine that this circle is describing the motion of some object, and at any given point in time, I guess I'll start with red here. At any given point in time, let's say at this moment right here, the object is moving. It has a linear speed in this direction, tangent to the circle, right? This, in other words, this line here that I'm drawing, or trying to draw, is to represent the linear velocity at that moment. And ultimately, where we're getting right now, we now know, knowing something about Newton's laws, that one way of thinking of it is this is how the object is trying to move, right? It wants to go in a straight line. So it's moving in a circle because something is causing it or forcing it to move in a circle, but it wants to go in this linear velocity at this moment. And then we might have some later moment, like here, where the object is a linear velocity in this direction, v. So I'm drawing this thing moving clockwise, right? So here's, maybe I should call this V2, and I'll call this guy here V1. And so what has happened? Well, the speed hasn't changed, right? We said that this is uniform circular motion, so the speed hasn't changed. In other words, I could say if I'm calling this a velocity vector V1, and I'm calling this the velocity vector V2, then what I could say is the magnitude of V1 equals the magnitude of V2. They have the same speed, but clearly they're not the same vector, right? Because the direction has changed significantly here, right? V1 is going up at this angle, sort of up and to the right, and V2 looks like it's pretty much horizontal relative to the screen here. And so the direction has changed, and so what has happened? Well, there's been some sort of an acceleration. And it's this acceleration that I'd like to try to see if we can figure out. So let's just remember, obviously we know acceleration is defined as the change in velocity over the change in time. And so I'm curious to know what the nature of this delta V is. What's going on? How is V changing? What is the nature of this term delta V? And so what I'm going to do, this isn't really a proof, but it's kind of a nice visual demonstration, is I'm going to redraw this vector arrow to the best of my ability over here. So that's V1. And then I'm going to try to draw this vector arrow to the best of my ability so that they are tail to tail. It's not that good, is it? That's V2. And if I draw V1 and V2, well then I could represent delta V. Delta V can be represented, try to pick another color here, maybe green would be nice. Delta V is represented by this vector from here to here. That is delta V. And so now if I go ahead, this is so V1, V2, change in V, delta V. Now if I go ahead and transpose this vector, this green vector, delta V, onto my picture, you can see that it's pointing, but if I'm going to imagine a point here between V1 and V2, because this is the average delta V for this interval. And if we think about transposing this arrow here, it's going to look like this, which is to say it's pointing very roughly, or actually, if I was really precise, it would be pointing exactly to the center of our circle. This is our center point right here, pointing exactly to the center. which seems to imply that the direction of the change in velocity vector, the delta v vector, is towards the center of the circle. And just not to belabor the point too much, but we could go ahead and I'll use yellow. We could go ahead and do another. We could do v3 down here and do the same argument, right? Here's v3. I'm not sure how well that yellow is showing up, but and now I could go ahead and put v3. I'll put v3 right here. And now my delta v, in this case, right, is like this. Here's the delta v now, which if I transpose it here is right there, delta v. So the delta v, if we keep going around the circle, we're going to keep coming up with our delta v vector as pointed towards the center of the circle. And there's a fancy word in Latin meaning towards the center or center seeking, and that word is centripetal. And so we call this a centripetal acceleration. And again, this word centripetal is a word that means center seeking. Centra meaning center, pedal meaning seeking. So this is center seeking. Oh. Center seeking, or towards the center. This word, don't get this word centripetal confused with this other word, which is centrifugal. Centrifugal, which is a word that you probably hear more frequently, is a word that means center fleeing or away from the center. So it's exactly the opposite of centripetal. Centrifugal would seem to imply some sort of a vector going radially outwards away from the center. And actually, frequently when people say this word centrifugal in everyday speech, they're referring to something that's fictitious. And I might have a chance to talk about that in a minute, but they're referring to something that doesn't really exist. And so this is the centripetal acceleration that we're talking about, or towards the center acceleration. And the centripetal acceleration, which we'll abbreviate A sub c here, if the scalar value or the magnitude of the centripetal acceleration is given by, and I'm just going to sort of tell you this, and I might hopefully have a chance to put out a later video that will actually give you a proof, because it's an interesting proof, but this is equal to the speed, the linear speed, v squared divided by r, the radius of the circle. This is the scalar value of the centripetal acceleration. Okay. Another way you might say this, because this centripetal acceleration is a vector quantity, but what we would say is the magnitude of the centripetal acceleration is equal to the magnitude of so I screwed that up, didn't I? The magnitude of v, the velocity, squared divided by r. So this is sort of definition, and I'm just sort of giving this to you, and later on, hopefully, I can prove it. And the unit here, of course, our unit is our standard unit for linear acceleration. This is a linear acceleration, so meters per second squared. And again, remember what v is. V is, when we're talking about v, this is the speed, the linear speed that the object has as it's moving around this circle. Okay, that's what we mean by v. So for right now, this is our expression for centripetal acceleration, acceleration towards the center. One other thing that I'll point out now, because we will use this later, is another way you could measure the motion of this object as it moves around the circle. Another way you could think of it is it's moving around the circle, and we could come up with an expression that talks about the time it takes to move in a circle. And that time, t, is known as the period. So let's think about the period. This is pretty straightforward, I think. The period, abbreviated t, if we imagine it for this circle, is simply going to be the linear distance to go around the circle divided by the speed with which the object is moving. So what is this linear distance? Well, that's just the circumference of the circle, 2 pi r. And so I can say the period t, oh, let me do this in black, be consistent. The period t is equal to the circumference, 2 pi r, divided by the speed v, right? This is what I'm saying here. I'm using this equation. T equals distance over speed, velocity. So 2 pi r is the linear distance, and v is the speed with which the object's moving. So that gives us an expression for the period. Okay. All right, so that's sort of in the abstract, an equation for centripetal acceleration, equation for period. Let's think about this maybe in a more specific case. Let's imagine, here's my circle again, and now I'm going to imagine that what we've got here in this circle is let's imagine you're looking down, and here this is some person here. This person is, you're looking down on them. That's their head. You see their nose right there, and this is the person's shoulders, and the person is swinging. Here's his arm. He's holding on to a rope. So here's this rope. Do it in blue, I guess. Here's this rope, and on the end of the rope is a rock. So he's holding onto this rope, and he's swinging this rock around his head. And let's just imagine that he's swinging it in an arc that is counterclockwise. So, in other words, this is the linear speed of the rock at this particular moment, right? And so then later on, when the rock is, let's say here, it would have a linear speed in this direction. And later on, when the rock is, say, down here, it will have a linear speed. So this is the linear speed v. We'll have linear speed in this direction. So it's moving in this counterclockwise circle. And we can, just for the sake of simplicity, let's remember that we're thinking about uniform circular motion. So this v is not changing. It's moving at constant speed. And so it might be interesting to think about if this rock is moving in a circle, it's accelerating, right? It is experiencing a centripetal acceleration. So this rock is undergoing a centripetal acceleration. And we know now that acceleration requires a force, right? Acceleration is equal to force over mass. And so if the thing is accelerating, it must be experiencing a force. So this centripetal acceleration requires a centripetal force. Okay, we know that this comes out of our understanding of force and its effect on motion. So we can say absolutely that this centripetal acceleration that the rock is experiencing requires a force. And in this case, it's really not hard at all to imagine where this force is coming from, right? It's clearly coming from the rope. So I don't know if you can see this green. Here is this, the rope is pulling inward on the rock, right? The rope is pulling inward, and that is the centripetal force Fc. So it's a centripetal force, so we shouldn't be surprised that the direction of the force vector is towards the middle, right? Towards the center of the circle, right? Here's the center of the circle. Because if it's centripetal, then it must be center-seeking. And the centripetal force is indeed directed radially inward, which again makes perfect sense because that's the direction at any given point in time. If I were to draw the rope, right, at any given point in time, the rope is going to be directed inward, radially inward towards the center. And so the centripetal force at any given point in time is going to be directed radially inward as well. F sub c. So this is the centripetal force, and we know that general expression for force out of A equals F over m, we can say that the general expression for a force is F equals ma. And so now what we can say is the centripetal force F sub c is equal to the mass of the object accelerating times its centripetal acceleration, A sub c. And since we know that we have an expression for A sub c, v squared over r, I can go ahead and rewrite this whole thing, m v squared over r. And now we have an expression for centripetal force. And this is a very useful expression because in the real world there are lots of cases of centripetal forces, and it's sort of interesting sometimes to think about what they are. Before I move on to talk a little bit more about some everyday centripetal forces, let me go back to this this fictitious force, what I mentioned earlier. I mentioned the centrifugal force. Okay, and I mentioned this is frequently this is sometimes called a fictitious force because usually when people imagine the centrifugal force, they're imagining something that doesn't really exist. So I would invite you to imagine that you're this guy. This guy right here is you. Okay, and you're swinging this rope around your head, right? You're swinging it in this horizontal circle, and there's a weight. This rock is on the end of the rope. And what are you going to feel? Well, you are going to feel, so maybe I'll just draw you here. This is you. What do you feel as you do this? So here's your arm, that's your shoulder, and here's your arm. And you're holding onto this rope. Well, you feel an outward pull. You feel a pull this way on your arm. And I guess this force here is the force on you, right? And so what people imagine frequently when they feel this tugging on their arm outward, they imagine that there's a force, therefore, on the rock pulling the rock outward, right? So the argument is, so I'm drawing this would be our centrifugal force, right? They imagine, all right, well, if I'm feeling the rope pull out of my arm, then that must mean that there's an outward force on the rock, which is pulling the rock and the rope away from the center. So what's wrong with this argument? Well, first of all, you should immediately, knowing something about Newton's laws now, we should immediately realize that this force can't exist. This has to be nonsense because there's no agent. There's nothing that's pulling the rock outwards, right? There's nothing here to pull it outwards. Forces don't come from nowhere. They come from some agent. And there's no agent pulling the rock outward. There's nothing pulling out this way, right? Nothing pulling out this way. So there is no centrifugal force. So why do you feel this outward pull? And maybe you can see now that this outward pull on your hand is really just a reaction force. Okay? So the rope pulls the rock inward. And when the rope pulls the rock inward, the rock pulls the rope outwards. So when you pull in on the rope pulls outward on you. So this force, F, does apply to you. There is a force pulling your arm outward, but that does not mean that there's a centrifugal force on the rock. And frequently when people use this word, centrifugal force, what they're mistaking is the fact that this outward pull on their hand which is in a sense centrifugal, right? It is away from the center in a certain sense. But that centrifugal force is not being applied to the rock itself. So just a cautionary tale on the use of that word. All right, well that's sort of a good introduction, but I'd like to spend a moment here and just think about some examples of centrifugal forces. So we just had a centrifugal force, which was a rope pulling on a rock, and it wasn't hard to see the centrifugal force in that case, but let's come up with some other ones where it's a little bit harder. Maybe not too hard, but here's the sun. Let's say that we have the sun here. This is the sun. And circling the sun is the earth. Here's the earth. The earth, you guys probably all do know that the earth doesn't actually move in a circle, but let's assume for the sake of simplicity right now that it does, that it's moving in a uniform circular orbit around the sun. And the question is, why does it do this, right? The earth, of course, at the moment here, has a linear speed v upwards in all objects. The earth is an object after all with mass, and all objects with mass want to go in straight lines. So why doesn't the earth go off in this straight line path? What keeps it moving in a circle? In other words, what is this centripetal inward force? And you guys have no difficulty imagining what this centripetal force is. You know that the sun pulls on the earth. In other words, in this case, gravity is a centripetal force. Okay, so that's a case where gravity is acting as the centripetal force. I invite you to think a little bit deeper on this and realize that there's something sort of mystical about this, right? Because it's easy to see the rope pulling on the rock in the previous example, but in this case you're imagining that the sun is literally pulling on the Earth. And by the way, pulling very, very hard. The Earth is really massive, and it's not easy to get a really massive object to accelerate. So the sun is pulling very, very hard on the Earth, but it does this through a vast expanse of empty space. And it's sort of interesting to think about where this sort of invisible force is coming from. But just for right now, recognize that gravity is frequently a centripetal force. Okay, let's think about another one. All right, now let's imagine we have a car. So here's our car. Here's this car. Here are the tires of the car. Right? We've got tires, and we're looking down on the car, and the car is making is moving in a circle. Maybe it's going around this traffic circle, this rotary. And again, like all objects, the car has a linear speed, and like all massive objects, it wants to move in this straight line. So in this case, if the car is moving in a circle, again, there must be some centripetal force. Now, what is, in this case, what is the centripetal force keeping the car moving in a circle? And maybe this isn't immediately obvious, but I would invite you to think about under what circumstances, if you were driving, would you try to turn but fail to do so? And you might be able to imagine a situation where you're driving down the road on a winter's day and the road is very icy, and you go to make a turn, you turn your wheel, and the car continues in a straight line. Maybe some of you have had this happen before, and you ask yourself, well, what happened? When I turned the wheel, why didn't the car turn? And you know that it has something to do with the icy road and the inability of your tires to get traction on that icy road. And what you're really keying in on here is that what's allowing you to turn is friction. We call it traction sometimes, but really we're talking about friction between the tires and the road. So friction is the centripetal force. And this is also a common occurrence where you have friction acting as a centripetal force. Okay, last example. How do I want to do this? Let's imagine I know how we'll do this. So here's our circle again, and what I'm going to imagine, some of you may have done an amusement ride like this, where you stand with your back against a wall. So we're gonna look down on you again. Here you are, and we're looking down on you. Here are your shoulders, and you're facing the middle of this circular room, right? And your back is to the wall. This is the circle perimeter is imagining the wall. So you're in this circular room. And what happens is, as you stand there, the room starts to move in a circle. So the room starts to spin, and you're standing there, and you are spinning with the room. And of course, and actually, what's interesting, and we can talk about this later, but the way this ride works, if you've done this ride at an amusement park, is the room spins faster and faster and faster, and then once it reaches a certain speed, the floor drops out from underneath you, and you find yourself pinned against gravity, against the wall. And that's a different question. What keeps you pinned against the wall? Why don't you slip down the wall? And that's due to the friction, right? There's some friction here between your back and the wall that keeps you from sliding down. What I want to think about is why, in this case, if your body has a linear speed this way, what keeps you from moving off in that straight line path? And any child would say, well, I don't go in a straight line path because the wall is there, right? The wall is literally pushing you inward. And so you know that, but what would we call this? Well, this force now, centripetal force, if we imagine the circle as a wall, is always perpendicular to the surface, perpendicular to the wall, right? It's always, by definition, the centripetal force, the radius is perpendicular to the surface. And so what this is actually a normal force. Normal force is the centripetal force in this case. So there are other examples, but I just wanted to go through some common examples of Centripetal force is normal force. Here can be a centripetal force, or friction can be a centripetal force. Gravity, we didn't label it, but maybe it's obvious in this other case down here. What was the centripetal force here? Well, in this case, tension, right? Tension. The tension in the rope is the centripetal force. So that's it for now, just an introduction of centripetal acceleration and centripetal forces. Hopefully I'll have a chance to give you a video later on that proves this relationship, right? I just sort of gave this to you, but I'd like to prove this. So if I have a chance later on, we'll have a proof of that.